In this presentation, I am going to explain four-quadrant operation of electric drive. Let us see four-quadrant operation of motor driving hoist load. That is, what are the motor four-quadrant operation of a motor which is driving a hoist type of load. Now coming to the four-quadrant operation, in mechanical plane, as we are aware, torque is taken on the x-axis, omega m is taken on the y-axis. If torque and omega m both are positive, then T into omega m, that is positive, and this plane or this quadrant is what we call it as forward motoring. Therefore, if omega is positive, we call it as forward, and if omega is negative, we call reverse, and if the product T into omega m is positive, we call motoring, and if T into omega is negative, we call it as braking. Based on that one, if this is omega is positive and T into omega is positive, that is which is called the forward motoring. And the second quadrant, omega m is positive and T into omega m, T is negative and omega m plus T into omega m is negative, that is called, it's called a braking and forward braking. And the third quadrant is, second quadrant this one, third quadrant is torque is negative as well as omega m is also negative. Therefore, T into omega m is positive. That is called, it is a reverse motoring. The fourth quadrant is torque is positive and omega m is negative. Therefore, T into omega m is negative. That's called the braking action. And since omega m is negative, it is called reverse braking. Therefore, these are the four quadrants of operation: forward motoring, forward braking, reverse motoring, and reverse braking. Now, how can this motor driving a hoist can be operated in this four quadrant? This is the first quadrant, and this is the second quadrant, third quadrant, and fourth quadrant. Therefore, coming to this, it consists of a rope wound on a drum coupled to a motor shaft. That is, a drum is the, let's say, motor that is coupled to a motor shaft. And one end of the rope is tied to a cage which is used to transport man or material from one level to another. This is the cage that can be used to transport either material or man from lower level to the upper level. And weight of a counterweight, there will be a counterweight, and the weight of the counterweight is chosen to be more than the weight of an empty cage but less than a fully loaded cage. That is, the weight, the counterweight is, it is more than the unloaded cage and less than the loaded cage. So such a counterweight is chosen. Now, motor speed omega m is positive when it rotates in the forward direction. That is, it is in anti-clockwise, but we are taking it is an anti-clockwise. If motor is running in the anti-clockwise direction, that is taken as positive. And if omega m is negative, motor drives in the reverse direction, and that is taken as the clockwise direction. The clockwise direction of the rotation is taken as the reverse direction. That is, here omega m is negative. Therefore, if it is running in clockwise direction, it is taken as a negative, and if it is running in if omega m is positive, then motor that will be running in a anti-clockwise direction. Now, if motor torque T is an anti-clockwise, the torque produced by the motor is in anti-clockwise, T is taken as positive. And if the motor torque is in clockwise, T is taken as negative. Therefore, if the motor is running in anti-clockwise direction, omega m is taken as positive, and the torque is also taken as, if torque is also clockwise, so anti-clockwise, it is taken as positive. Now, if the motor is running in clockwise direction, omega m is taken as negative, and if torque is acting in a clockwise direction, it is taken as negative. These are the polarities of T and omega m. Continuing for quadrant operation of a DC motor driving a hoist load. First quadrant of operation, as I already explained, this is the first quadrant of operation. That is what we call it as forward motoring. In that case, the loaded cage is moving upward. This is a loaded cage that is moving upward. That is the process that is done in a forward motoring. Therefore, since the loaded cage is more than the counterweight, the load torque TL acts in the clockwise direction. Therefore, loaded cage is this weight is more than this one. Therefore, the load torque will be acting in a clockwise direction. Always the motor torque will be opposite to the load torque. Therefore, the motor torque will be in a anti-clockwise direction. So the motor torque will be in anti-clockwise direction. And since the loaded cage is moving upward, omega m will be in anti-clockwise direction. That is also positive, meaning that both both the torque produced by the motor and omega m both are positive, because both are, we can say that is equal to anti-clockwise direction. Therefore, both are, since T and omega m positive, T into omega m is positive, and as omega m is also positive, therefore here it is called forward motoring operation. Therefore, a loaded cage moving from lower level to the upper level, the motor is working in a forward motoring operation. Both torque and omega m are positive. In second quadrant of operation, that is taking place when an empty cage is moving upward. That is here, an empty cage is moving upward. The motor is working in the second quadrant, that is forward braking mode. Let us see that one. Now we have seen that counter weight of this counter, this one, the counter weight is more than unloaded cage. Since this is more than unloaded cage, net load torque will be in the anti-clockwise direction. That net load torque will be, and therefore the load torque will be in anti-clockwise. Since the load torque is in anti-clockwise direction, motor torque will be opposite to load torque, that is will be in clockwise direction. And since and that is why the motor torque will be in clockwise direction, that will be negative. And since the cage is moving upward here, is moving upward, as we have seen that omega m will be also in anti-clockwise direction. That is, omega m will be positive and the motor torque will be negative, and the motor torque will be negative. Therefore, T into omega m, that product will be negative. Since T is negative and omega m is positive, T into omega m will be negative, or power is negative. That means that it's a braking operation. And since omega m is also positive, that indicates it's a forward. That is why it is called forward braking. Therefore, the second quadrant of operation, forward braking operation, is taking place when an empty cage is moving from the lower level into the upper level. Continuing the fourth quadrant operation of a motor driving a horse here, let us see next one, quadrant 3. Quadrant 3, as you know, this is the reverse motoring region, or this is a reverse motoring quadrant and such. That is this one, reverse motoring. In that case, the unloaded cage is going from the upper level to the lower level. The unloaded cage is moving in this direction. And since, as you know, that one, the counterweight is more than the unloaded cage, this weight is more than this one. Therefore, the load torque will be in this direction. Load torque will be in anti-clockwise direction. Sorry, load torque will be in here. This will be more than this one. Therefore, here, so the counterweight is more than the empty weight, and the load torque acts in anti-clockwise direction. So the motor torque will become in clockwise direction. Since load torque is acting in anti-clockwise direction, the motor torque will be in clockwise direction, meaning that the motor torque is taken as, the sign of the motor torque is taken as negative. And since again here this weight is the cage is, unloaded cage is moving downwards, then we can say that this omega m is also negative. This omega m is negative. Omega m here, it is equal to in clockwise direction. Omega will be in clockwise direction, that will be negative. So Tm, motor torque is negative. The same time, omega m is also negative, or T into omega m will be positive, or the power is positive, means that again it's a motoring operation. If the product is positive, it calls motoring operation. If product is negative, it calls a braking operation. Therefore, in this case, since T is negative and omega m is negative, the product is positive. That is why it is a motoring operation. But since omega is negative, it is called the reverse motoring. Therefore, this quadrant of operation is called reverse motoring. That is why an unloaded cage is moving from upper level into the lower level. That process, during that process, the motor is working in a reverse motoring operation, or in a third quadrant operation, in this third quadrant operation. Continuing the fourth quadrant operation of a motor which is driving a hoist type of load, again the fourth quadrant of operation, you know that fourth quadrant of operation is this one, that is the reverse braking operation. It's called the reverse braking. Again here, as you know that loaded cage, in this case the loaded cage is moving upward, that is the loaded cage is moving downwards. That is, the loaded cage is moving from the upper level to the lower level. That is, loaded cage is moving downwards here. And since the loaded cage weight is more than the counterweight here, the net load torque will be in this direction, or in this direction means it will be in the clockwise direction. And since the load torque is in the clockwise direction, and motor torque will be in opposite, that is in anti-clockwise direction. Therefore, the motor torque will be in anti-clockwise direction means that torque is positive. And again, omega m means that here this is moving downward direction. Since this is moving downward direction, and here omega m is also in clockwise direction. Omega m will be in clockwise direction. That's negative. Therefore, omega m is negative and the motor torque is positive. That is why T into omega m will be equal to negative. And since omega is negative, it is called a reverse. That's why reverse braking operation. Therefore, since the loaded cage weight is more than the counterweight, load torque acts, TL acts in clockwise direction. Always motor torque will be opposite to the load torque. That's why we know it. So the motor torque will be in anti-clockwise direction. And the motor torque, that T, capital T, that is called in anti-clockwise direction. And since the loaded cage is moving downward, that is omega m will be in clockwise direction. Since the load is moving here, omega m will be in clockwise direction. In clockwise direction means it will be negative. Therefore, omega m will be negative and the motor torque produced, that is equal to positive, or T into omega m is negative. And that it is negative power, or you can say that it is called the braking operation. And since omega is negative, it is called the reverse. That is why this mode of operation, that is the fourth quadrant mode of operation, we call it as reverse braking operation. Therefore, when a loaded cage is moving from the upper floor or upper level into the lower level, the motor is working in the fourth quadrant. That is what we call it as reverse braking operation. That is the fourth quadrant it is working. Coming to a problem, a weight of 500 kg is being lifted up at a uniform speed of 1.5 meter per second by a winch driven by a motor running at a speed of 1000 rpm. This is a motor and this is a winch and this is a weight that is moving. The moment of inertia of the motor and the winch are 0.5 and 0.3 kilogram meter square. This is 0.5 and this for this one it is equal to 0.3 respectively. Calculate the motor torque and the equivalent moment of inertia referred to the motor shaft in the absence of weight. Motor develops a torque of 100 Newton meter when running at 1000 rpm. Now coming to the solution, first let us see what is the angular speed omega m. Omega m is nothing but omega m equal to 2 pi n divided by 60. 2 pi into speed is equal to 1000 rpm. 2 pi into 1000 divided by 60. 104.72 radians per second. This is the angular speed omega m. Now to find out the equivalent moment of inertia, normally what we used to do is equating the kinetic energy. Therefore, half into j into omega m1 square, where capital J is the equivalent moment of inertia. Half j omega m square equal to, what is the moment of inertia? What is the kinetic energy associated with this one? Half jm omega m square plus half jw, that is this. We are connecting a winch, that is the moment of inertia of winch. Therefore, half jw omega m square plus half mv square, that is the kinetic energy associated with this one. And substituting this one, half j omega m is equal to 104.72 radians per second square equal to half 0.5 into 104.72 square plus half 0.3 into 104.72 square plus half mv square, mass equal to 500. It is equal to we are getting it is equal to where it is that the 0.3 respectively. Here we have to substitute in this one that much kilogram. We can, this is a 500 kilogram. This one it is a 500 kilogram into this is a meter per second second, that is the velocity 1.5 square. Substituting that, equating this one, you'll be getting the moment of inertia, equivalent moment of inertia from this equation. You'll be getting it is equal to 0.9026 kilogram meter square. continuing this problem. In order to find out the equivalent torque, T, we are equating the power. Therefore, equivalent torque equal to T into omega m equal to the torque produced by the motor, Tm into omega m plus that load side, that motor, that weight. Therefore, that is equal to force into velocity, F into V. This is the basic equation equating the power. And from this one, you can find out what is the unknown, that is equivalent torque. T into this omega m 104.72 equal to Tm is given as 100 Newton meter. That is into omega m 104.72 radians per second plus that is m, that is the mass 500 kilogram into 9 into g, that is called, that will be converting into F, and that into velocity 1.5. and equating this one, you will be getting the equivalent torque is equal to 170 plus 0.26 Newton meter. For the equivalent torque equal to 170.26 Newton meter.